This is Lab 7 on Flexure and Strain by Christian Serafin, Dylan Maria Alvarez, and Benjamin Romanek. In this lab, we're exploring more complex loading, bending, and comparing more precise measurements with a strain gauge against crosshead displacement. This is to compare the bending stiffness calculated using both measurements and accompanying beam theory. Materials tested in this lab will just be polycarbonate. Initially, we will measure the length of the beam, width of the beam, and thickness of the beam. And this will give us measurements to use to scale our data with. We will clean the surface of the beam using a degreaser and then sand it with light grit sandpaper to create a rougher surface for our adhesive to work on. We'll then wipe away any debris with alcohol wipe and scratch a mark in the middle of the beam, both lengthwise and widthwise, so that we know where to place the sensor. We'll place the sensor, the front of it, on a piece of Scotch tape and add a small dab of glue to the back and place that sensor right on the mark we just made on the beam. The adhesive will be, the piece will be held on with the thumb for a couple of seconds to make sure the adhesive sets, and then the tape will be finished wrapping around. We'll tape the wires somewhere else along the beam to make sure that they don't get bent or otherwise damaged during testing to minimize errors. We'll strip the ends of the wire and connect them to the screw terminals that lead to the benchtop multimeter. We'll calculate the measured strain epsilon and compare it to the expected strain calculated using beam theory. Epsilon equals y over r, where y is the distance from the neutral axis and r is the radius of the curvature. We'll make multiple measurements and dimensions to calculate the average and standard deviation, and we'll measure displacement, strain gauge output, and load.
This results in discussion for the deformed beam. It is recognizable that the math calculations mz equals p over 2x required to derive this graph match the shape of the bend relative to the bending experiment done in class. This is because the least force resistance lies near the middle, where the sides have the most force resistance because they lie on a fixed point, while the center holds no support. A similar version of this experiment is shown to the right of the graph for reference. Notice the bend in the material. This is the stress versus strain graph, results in discussion. The stress strain graph depicts the relationship between the stress, applied force per unit area, and the strain, deformation, and polycarbonate as it is subjected to mechanical forces. These graphs provide important information such as Young's modulus. This is the results in discussion of the low displacement curve. A low displacement curve is a graphical representation that illustrates the relationship between the applied load and resultant displacement in a material or structure. As force increases, so does displacement. This curve is used in materials testing and engineering to assess mechanical properties, validate designs, and ensure structural safety, making it a crucial tool for understanding how materials respond to applied forces and loads. This is the results in discussion for Young's modulus. Young's modulus shows the stiffness of a given material, which is useful information for engineers and anyone in product design. Since the Young's modulus is so low, we know that the material is easily bent. 1 represents Young's modulus from the web. 2 represents the stress strain Young's modulus grabbed from graph stress strain. And 3 represents the displacement load graph Young's modulus.
Result and discussion for data. Data table 1 represents the calculation necessary to determine the stress for the stress strain graph in slide 8. Data table 2 depicts the necessary values used to calculate the strain data, which is represented how the object deformed during the given stress. Conclusion. We were able to accomplish a number of important goals in the experiment, such as learning about the strain gauge attachment method, utilizing strain gauge to measure the strain relative voltage, familiarize ourselves with flexure beam bending testing, using theoretical equations to compare experimental beam bending behavior to theoretical predictions. In the field of material science and engineering, these abilities are extremely valuable because they enable us to reduce potential source of error, design stronger structurals and make well-informed decisions that improve material performance and relativity. Future work recommendations. In the future, this lab should add another material from another family, like a metal, to be used to show how different material reacts to be in the same situation. If a material cannot be given, the data of it is enough for students to see how they react differently and similarly for the polymer through an NC lab. References. The formula was given to us in lab manual 7, while the young modulus was found using the NC.com.